Good morning, everyone. Are there any questions from the previous lecture? Okay. So we'll quickly revise what we discussed in the previous lecture before going on to today's topic. In the previous lecture, we said that let us assume that we've been given a data set and we're trying to fit a univariate normal distribution to it. So we're trying to figure out the parameters mu and sigma, which we feel will best define the data set or best describe the data set. So we do so by first writing out the PDF corresponding to the normal distribution, and then we write the likelihood function. And importantly, we can factorize the likelihood as a product of the individual PDFs. Can someone again quickly tell why this is the case? Because of what? Because of IID, we can break down this likelihood term as the product of individual PDFs evaluated at the corresponding excise. And then we can also correspondingly get the log likelihood function, which we are trying to maximize. So maximizing the likelihood is equivalent to maximizing the log likelihood, which is equivalent to minimizing the negative log likelihood, which is what you're trying to do in your assignment. Right? While analytically, when we're solving it, we're trying to just maximize the log likelihood. But for your assignments, typically, whenever we're solving any optimization problem, we are using gradient descent, which means we're trying to find a minima. And we wrote that this is the log likelihood function for normally distributed data. It has a term, one term which is a constant, two terms containing sigma, and only one term containing mu. And through this, we are able to obtain mu MLE to be the average of the data, and sigma square MLE to be the variance of the data. But importantly, we said that this variance is biased. Right? So it's biased in what direction? Is it an underestimation or is it an overestimation? It's an underestimation. Why? Can someone tell why? So we are given some samples and not the entire population. Because we are given some samples, it is possible that the samples do not have the full coverage as the population. In this case, the samples are only going from 0 to 1.1, whereas the range of the full samples is the real number line. So if we were to consider different samples, we'll see that the sigma is often underestimated in these. And then we looked at this very interesting plot, which shows over the 100 different data sets, subsets of the population that we could have obtained. We see that the mu's are fairly spread, but the mu's, if we were to take an expectation over these mu's arising from different data sets of size 3, they would converge to approximately close to 0. Whereas if we were to consider the expectation of sigma square, that is severely underestimated in comparison to the actual population standard deviation or variance, which was 1. And then we saw that as we increase the dataset size, a few things happen. What happens to the spread along the x-axis? What happens to the spread along the x-axis? The spread decreases as you increase the size of the dataset that you're having, but the mean still remains unbiased. So that is important. While the spread of the estimator will reduce, it is still an unbiased estimator. Whereas if we consider the sigma square estimator, we now observe that the expectation of sigma square has got much closer to the true value of 1. So the bias in the estimator has been reduced as we've increased the number of samples we're drawing. And then we saw that as we go to a very large sample size, we have sample size of 100. Now the variance in mu hat estimator has been reduced very significantly. The expectation is still unbiased, so it's an unbiased estimator, whereas the sigma square is also now almost an unbiased estimator. There's a very minimal bias. And then we saw that if we look at the estimated standard deviation, it seems to be a function of n. As we increase n, the estimated standard deviation gets closer to the true value. And we said that perhaps there is a simple function which we can use to transform this estimated standard deviation into corrected standard deviation or the population standard deviation. That turned out to be n divided by n minus 1. So if we do n by n minus 1 correction factor, we get a very nice corrected standard deviation. And then we looked at some mathematical properties where we could have proved this. I'd mentioned that we had also looked at then the bias and variance in context of machine learning, which we had studied. And we had also discussed about bias and estimator in the context of stochastic gradient descent. Is the SGD estimator a biased estimate or an unbiased estimate? Unbiased. What are we trying to estimate? The gradient. We're trying to estimate the gradient from a single sample. And we're saying that if we consider all the possible samples, so the expectation of the gradient calculated over a single sample is the same as the gradient calculated over all the samples. So therefore, SGD is an unbiased estimator. Therefore, it makes a lot of sense to use SGD. But importantly, a few slides back, we saw that something being unbiased doesn't necessarily mean it's a very good estimator, because we also have to consider the variance of the estimator. And in this case, when we're considering normal distribution, we see that as we're increasing the size of the samples that we're drawing, the variance is reducing. So the estimate is getting better, which sounds intuitive, because if you have a lot of samples, you're getting closer to the population. You've been able to draw a lot of samples. Okay, any questions on this?
We said that sigma square from MLE is biased, but we did not discuss why it is biased.
So we've been discussing that for the. So it's biased because we are trying to estimate a quantity from samples, and we're trying to measure. We're trying to estimate them to be as close as possible to the population characteristic. Right? When we draw certain samples. So if we draw certain samples, so we're looking at these samples. Let's go to sample size 3. Or let's start with sample size 4. You see the spread here is from -1 to 1. What is the spread of samples if you were to draw them from the population? -infinity to +infinity. They're over the entire real number line. So we are not going to be able to span the entire set of possible values. So therefore, through samples, we'll be underestimating the variance. So that's the geometric sense, or the intuitive way to understand this based on these graphics. And we can also mathematically prove the same, which I had left as an exercise. I had pointed out certain resources. You can do that in one time. But the important thing to consider here is that all of these considerations are important only when the sample size is small. For large sample size, n over n minus 1 is almost 1. So these things are not particularly important in that case. Number of data sets? If you increase the number of data sets, you don't get any advantage, because the expectation will. So that's what we're doing. So if we increase, so in this case, these plots that have been created, these have been created over 100 different data sets. Right? Some of them will give you variance very close to 0. Some of them will give you high variance. Most of them will give you very low variance, much low variance than the true variance. But increasing these number of trials is not going to help you. No.
So, as we increase the sample size, like this spread decreases, and the
expectation of sigma square becomes better, becomes closer to the original value of coming from the population, which is 1. Right. Right. So let's see. You consider sample size equal to 3. Consider these values. What are the ranges? -1 to -0.8. Right? This is if the size is 3. Now let's go and see sample size equal to 10. What is the range of values that you're observing? -2.5 to 2.5, much larger. So you're able to capture the endpoints better if you consider a larger sample size. Therefore, you'll be able to match better. So that's the intuitive way to get it. Again, we can prove it mathematically also. Which is good. If the spread is increasing, the spread of the data points is increasing, which means that sigma square is also increasing from this sample. Right? So the procedure again is that you're given a sample, you are given this particular sample. 10 points. What is the sigma square from these 10 points? 1.55. But instead, if you were given these 3 points, this is your sample, then the sigma square is 0.12, right? So if the sample size is small, it's much more likely that you'll not be able to span the whole range. With sample size being very, very large, it's much more likely that you'll be able to get extreme values, which also means that you'll be able to estimate sigma square better, right? Any follow up to that? Convinced?
Like in mu and sigma plot, you said that the spread is decreasing.
So mu and sigma, what I was talking about is, let's look at this plot again. I'm first just concentrate on the x-axis, right? The x-axis is the estimation of mu hat, right? For we have 100 such data sets of sample size 3. For one such data set, mu hat is 0.0. For another such data set, it is -1. For another data set, is 1.0. So if you were to consider larger sample sizes, again the mean would also be better estimated. So if we go back, let's consider this data set of size 3. What is the mean? 0.76. It's very far from the true mean 0. This one, it's 0.68 minus 0.78, so the estimates are quite off. But if you were to average them, you'll still get 0. But if you instead had a larger sample size, 100, what is the mean? 0.07. What is the mean? 0.02. So this variance over these numbers, 0.02, 0.07, is what we're considering as the x-axis. Yes. Mm-hmm.
Let's say there is a case where we have the sample size is small, but the data sets are 1000.
Okay.
And in other case, the sample size is larger, but the data set is 100. Then would there be the estimation in sigma variance, the estimation in the variance, would it be close to the
Right. So the estimation in the estimate of sigma square, that is a function of this sample size, not the number of data sets.
But then, since these are IIT, so if I increase my data sets, then the
So even though you may be increasing your data set, you may still end up with, so let's say if you were to have, in this case you have 100 such data sets, right? So even if you had 1,000,000 such data sets, but the rough population would still be the similar, right? You'd have majority of them being below 1, you would have some of them being close to 1, and very few of them having sigma square greater than 3, right? So in proportion, these numbers will still hold, even though you may increase the number of such data sets. So it seems to be more important. So if you want to get a more unbiased estimate, you need to increase the number of samples you're considering while estimating this quantity. Right? So such things you can also just simulate, and you'll get a better sense of what is happening.
because I'm thinking that if I am running IIT, then increasing the data sets would include more number of samples from different people.
So if even though the sampling is IID, so because each of the estimate you are obtaining is still very biased, right? And that bias is coming because of the small sample size. So you will not be able to compensate that by doing more of wrong things does not get you a right thing. Right? Other follow-up questions? Now we'll come back to machine learning. Before that, we're trying to estimate some parameters of a distribution. We'll be talking about maximum likelihood estimate for linear regression. What are we trying to compute the estimate over? Over the model parameters theta. It would be very helpful to consider the generative view of the process. So we'd start with, let's assume that we somehow knew the true function, which had created the data, but we ended up with some noisy observations. Why do you think we get noise in the observations? Why are we not getting all the points along the blue line? The data is? The data is found from experiments, and the experiments have a certain bias or a certain observation bias which may exist, right? So how many of you have done certain experiments in your first year physics course and got them working perfectly? Even though you know the answer, even though you know the frequency of sound, you know the speed of sound, but are you able to get that exactly correctly? No, because there's some human observation and there's some instrument error, there's some human observation error, there is also some certain least count, right? Whenever you're talking about, you're trying to measure the temperature, right? What is the least count of the thermometers that we use? I'm talking about the analog ones, not the digital ones. 0.1 Fahrenheit, 0.1 Celsius, but that is perhaps not your exact temperature. Your exact temperature might be 98.123456789 something Fahrenheit. So there is some degree of imprecision over there, and because you're trying to look at it, so you might have struggled to get from the analog. How many of you use the analog thermometers? Good. With the mercury ones, is it easy to note exactly what the temperature is? You'll have to hold it at a certain angle. So there is a certain amount of bias, parallax effect, and certain amount of biases which may exist even in that. So because of all of these things, even though the relationship between x and y may be perfectly linear, the observations may often end up being with some added noise. Right? To keep a life simple, we generally say that the noise is coming. The noise is randomly distributed. By randomly distributed, it's normally distributed with mean 0 and a certain known variance. So this known variance you could attribute to, let's say, the instrument error or certain amount of observation error. Right? So this perhaps is the most important slide in the first part of this lecture. We have certain observations which are noisy, but we need to give them a certain amount of, we need to model that noise. See? So what we said is that particular noise is normal distribution with mean 0 and a certain known variance. Right? So this kind of noise is also known as, or this kind of linear regression is also known as homoscedastic linear regression. Can anyone now tell me why this particular model is called homoscedastic linear regression? Yes. So the skedasticity does not change as a function. This skedasticity or the dispersion or the variance is not a function of the input. It is constant. So irrespective of my x value, if you notice, the same noise is being added at each and every point, right, about the true functional value. So therefore, this is known as homoscedastic linear regression. Any situation where you think the homoscedasticity assumption may fail, where the noise itself is a function of the input. Here the noise is independent of the input. Yes. Yes. Right. So the variance could increase, decrease, change as a function of x, but in what circumstance might that happen? So let's talk about something simpler. The samples are still IID, but the noise is not is a function of x. Any practical scenario you could think where?
Like by focusing the uncertainty, as you move time.
Okay. Although that is coming, that particular noise could be coming because of your unknown model also. But we still, most of the times, I think we just assume that the distribution is still normal about it.
Like for example, we are using mercury for measuring temperature, but the thermal expansion coefficient of mercury is dependent on the.
Okay, excellent. So something where the underlying physics or the underlying phenomenon is itself going to be changing, or you're trying to model certain electronic components. You're trying to measure the photovoltaic energy generation as a function of the amount of, let's say, the amount of light which is following. But that function itself is highly complicated. It's non-linear, and it also introduces some amount of noises which become a function of the input x. Right? In this case, we'll assume the noise to be constant. It's a simple case. Homoscedastic linear regression. That's what we call this. Any question on this? So we again start with the same formulation. We are given a data set. Previously, whenever we were looking at a data set for estimating parameters, we only had one item, right, which is only the observation. Like in the case of coin tosses, we only had the coin flips, either heads or tails, or for the normal distribution, we only had the observations, which are again x, single x values. This time we have x's and y's. X are my input features, y are my observations, and x could be any d-dimensional vector, not necessarily a one-dimensional. That's my feature vector. And we are trying to consider a regression problem with this likelihood, normal likelihood. We say that the probability of y given x is given as a normal distribution in the variable y, whose mean is f of x and the variance is sigma square. Right, I want to go over these slides slightly slowly because it's important and we may miss the underlying point. Right, so we're saying that my probability of observing a certain y given an input x is a normal distribution whose mean is f of x. What is f of x? We'll come to in a second. And the variance is sigma square. So if we go back, so at what we're saying is that the probability of obtaining a certain y, let's concentrate to where my pointer is. Right, so my pointer is somewhere over here. Right, this is my f of x. Right, my f of x is coming from the line because I'm assuming a linear relationship. F of x is x transpose theta. Right, so this is f of x, the orange dot, but my y could lie anywhere along this axis. Right, I could have made observation anywhere along this axis. It is more likely to be very close to the line because we have made a normal distribution assumption, and the maximum mass of the normal distribution is at the mode, at the mean. Right, so it's most likely that the point will lie here, but it's highly probable that it could be away from this line itself. So that is the assumption that we have made. The other way to write this is that given x and y, we can write y equal to fx plus epsilon, where epsilon is normal distribution with mean 0 and variance sigma square. Right? So do you follow that going from y equal to fx plus epsilon, and what we had previously shown is following just the addition of two random variables. Right? So there is no uncertainty in estimating fx. The only uncertainty in estimating y as a function of x comes because of the randomly normally distributed noise that we've added, whose mean is 0 and whose variance is sigma square. Right? So think of it as you're trying to add something with mean fx and no variance with something with mean 0 and variance sigma square. Got a question?
Sir, in the previous slide, you had said the expression is probability y given x. So is x a parameter?
So x, so think of this as, I'll come to this in a second. I'll come to this, I have something specific there. Firstly, does everyone agree that fx equal to x transpose theta for linear regression? That is just theta naught plus theta 1x plus theta 2x2, so on and so forth. And this is the graphical model which will help us understand what is going on. You are given an xi, the ith data point, input for the ith data point. You are given theta. You can compute xi transpose theta, which is what you had been doing previously in the ML course also. Importantly, you don't end up at xi transpose theta. In the previous course, what did you write xi transpose theta equal to? Y hat, right? Our estimate was y hat equal to xi transpose theta, but for now we are not just considering the mean, we are considering that there could be some dispersion or some noise, sigma. So my yi is given as a normal distribution whose mean is xi transpose theta and there is some dispersion sigma, right? And for each xi, I get xi transpose theta using the common parameters theta and using the common noise parameter sigma, and through this I am able to obtain yi. Right? So this helps us understanding how the data might have been generated. Right? Any questions in this?
Y is our own prediction
So for now, let's assume that this is the data generative process. Right? Let's go back to some code and see what this might mean. I've tried to create the code to mimic the process that we'd seen earlier. I have firstly uniformly generated numbers between -1 and 1. And I've created a function f, which is my true function for now, which I'm saying is 3x plus 1. Right? What is true theta naught? 1, and true theta 1 is 3. So these are the parameters we would try to recover. I have a noise term, which is given as a normal distribution with mean 0 and scale 0.1. This is the standard deviation in this case and not variance. You'll have to be careful with what the library expects. And I'm generating 100 samples from it. Right? What kinds of samples am I generating? IID. Right? Each sample has nothing to do with the previous sample. So I've generated 100 such samples. My dataset was of size 100. My noise is of size 100. So the noise I'm adding is independent for each sample. It has nothing to do with the previous sample. There is no bias or no pattern which exists. Right? At the same time, I'm using the same distribution to get the noise. So this sampling, the noise, is you're adding in an IID fashion. Once you've done that, I create my true y, which is fx plus noise. Right? So this is the generative process. Start with x, you have some function x, f. In our case, the function f is a linear function. This is the true function theta naught plus theta 1x, and add some noise to it. Obtain y as a addition of fx and noise. If we were to just plot these, you'd see what we've been using previously in linear regression also. You have a true line and you have some noisy observations about that. Right? Yes, Ritik. Clear? So if we go back now, right? So now what we're trying to do is to, given this model, graphical model, we're trying to find out that theta which would best describe our dataset xi and yi. Right? We'll come to Ritik's question in a second. It should become implicitly clear. We have the likelihood which is given by P of d given theta in general. So this is the main distinction I've been trying to point out. Previous examples, d was just the observation directly. You had the coin tosses or you had the spread of the data coming from some normal distribution. So those were just scalar values you were looking at. Now your data set is what? X, comma y. X are vectors, y are scalars. That is the data set. And for purposes of computing likelihood, we will assume that x is fixed. Given a certain x, we are trying to then compute what is the probability of observing y. Right? X, we will not be looking at the variation over x, right? Because x is given to you in the form of your training examples. The quantity which is varying is y. Therefore, we will write this P of d given theta as P of y given x comma theta. Right? So x is considered to be known in this case. Is this clear?
But likelihood is the probability data given parameter.
Yes.
But here x should not be parameter.
X is a known thing here because we're not trying to, so we're given a certain data set. Right? We're not trying to compute all the possible data sets which could have existed. That is not the purpose. Our purpose is given this data set, I know the input x, I'm trying to see what the output y could have been, where the noise is coming in from, and what those parameters could have been. So you consider x to be fixed, known to you before the experiment is done. So think of this as you're trying to conduct an experiment and you have your experiment notebook. You have already written the x's at which you want to compute y. Now because of the function theta or the relationship which exists between y and x, you'll have the relationship between y and x as well as you'll have some observation noise. Right? So we write this P of d given theta term as P of y given x comma theta. X is assumed to be known beforehand or constant. which we can then nicely factorize as P of y1 to yn given x1 through xn comma theta. Right? This is just writing out them in the vectorial sense. Now, how do we get this particular term, which is this is the product of P of yi given xi comma theta? IID assumption again. So, does knowing x2 help you know y1? There is no relationship, right? And that's how we are able to use the IID assumption, and we are able to write the log, the likelihood as the product of the individual PDFs corresponding to yi given xi's. Right? Thus far, everything is same. The only thing we'll have to change in a frame of reference is that now instead of having scalars being our data set, we have a vector comma scalar tuples, but the vector x is known to us beforehand, and we're only trying to consider the variation in y. So we go back to the definition of MLE, which was maximize the likelihood, right, which is equivalent to maximizing the log likelihood, which is equivalent to minimizing the negative log likelihood. Right. So given the previous expression, we'll take the negative log and we'll get this expression. Minus log of P of y given x comma theta is minus log summation of P of yi minus log product of P of yi given xi comma theta. But because log of products is the sum of logs of the individual terms, so therefore we can write it in this fashion. It's the sum over I equal to 1 to n of over the data points of log of P of yi given xi comma theta. Now we can, to simplify the problem, let's consider a single data point x I and yi, and then we can just naturally just sum over this to get the term of interest. So for a given point xi comma yi, we can write it in this fashion, right? So this you have to prove on your own. Can you work this out in your notebooks? We know the PDF of the normal distribution. So let me first, if you want, you can take a snap. Right? So P of y given xi is a normal distribution with fx being x transpose xi transpose theta and a known variance sigma square. Right? So first we have, for a single data point, we can write like this, and then I wanted to compute negative log of P of yi given xi comma theta. So all you have to do is to write down the PDF for the normal distribution, right, and take the log of it, substitute the values of xi and yi's. Those who've been able to get this, you should then try and compute the negative log likelihood term and see what expression you get. If you need, you can just look up the PDF for normal distribution on Wikipedia and substitute that. Right. So let's start with this formula. Let's go step by step. So this is the PDF when the variable of concern is x, right? Our variable of concern is x or y? Y. We're looking at y. Can you first just substitute y here instead of x just to make your life simple? You'll get f of y equal to 1 upon root sigma, 1 upon sigma root 2 pi e to the power minus half x minus mu over sigma the whole square. What is the mu? Our mu is f of x, which is x transpose theta, right? If you put these terms and then you take a logarithmic of this quantity and you take a negative logarithmic of this quantity. So firstly, all of this term will be some constant, right? And you have some e to the power minus half x minus mu whole square upon sigma square. If you take the log of this, negative log of this, you'd get terms containing y minus x transpose theta time terms, right? Which will come to be something like, right, yi minus xi transpose theta. Any questions in this? You want me to repeat? So I know this gets a little confusing because whenever we think about normal distribution, we generally think in terms of variable x. Firstly, the variable we are considering the normal distribution is in y. We are considering the spread over the y-axis. We have to consider the mu. The mu here turns out to be a function of x, which is the mean value, most likely value, which is xi transpose theta. And you take a logarithmic, you will get something like 1 upon 2 sigma square yi minus xi transpose theta squared. Right. Now, if we sum over using the above formula, using this formula, if we sum over this ith term expression, we'd get something like 1 over 2 sigma square summation I equal to 1 to n yi minus xi transpose theta squared. And then if you were to vectorize it, you'd get 1 upon 2 sigma square y minus x theta transpose into y minus x theta, or you could write it as the L2 norm, square of the L2 norm of y minus x theta. Does this sound familiar to what we've seen earlier? Right. This is right. So there are certain constant terms, but we don't care about them because they do not involve thetas. So all we're trying to say is that, so actually this NLL of theta is equal to this plus some constant term. Optimizing NLL of theta equal to this plus some constant is equivalent to optimizing NLL of theta just considering this term, because that is the whole objective, that is the underlying principle. How is this similar or dissimilar to what we have seen in the previous ML course? So one, there we don't have anything like sigma in the ML course, right? What is the other thing that we have instead? We typically use what squared error? Sum of squared error or the mean squared error? Typically mean squared error, because that gets us independent of the size of the data set, right? So if we were to consider mean squared error, that would be just 1 over n y minus x theta transpose times y minus x theta, right? But all of those are just constants, right? We could, sigma square is a constant, we assume sigma to be known a priori, and we assume to be it to be a constant, and n is also just a normalizing, it's just a constant, right? So therefore, using this, we can say that the negative log likelihood is proportional to y minus x theta transpose times y minus x theta, which is the same as the objective that we had in linear regression in the previous course. When we were considering that, so we started off with the fact that we want our model to be very good, so therefore we wanted summation epsilon I squared to be as small as possible. That was the underlying motivation we started off. Here we took a more fundamental view in the sense that we thought about what could be the data generative process. We said that the data generative process is this graphical model. We have, for any input xi, we have the true parameters theta, and we combine them in a function f in a linear function form, which becomes xi transpose theta, which is the most likely value of our observation at that point. But because we have observation noise, therefore we assume our observations to be a normal distribution with the mean as xi transpose theta and certain variance sigma square, right? And all we are now trying to say is that given such data set of xi's and yi's, if we maximize the likelihood or equivalently maximize the log likelihood or equivalently minimize the negative log likelihood, we get an expression which is equivalent to what we had obtained in the previous ML course, which is just the mean squared error. Right? So now does it answer your question that why we end up using mean squared error? Why not mean absolute error, for example? That would have also been a good fit. So we get mean squared error from this line of thought because we assume that our yi's to be normally distributed about the line coming from the function, from the linear function. Right? If we had assumed it to be not normal, but let's say some other distribution, we'd get a different negative log likelihood, which would have then not been equivalent to the mean squared error. But that could also have been a perfectly valid way to solve this problem. Right? So we started with certain assumptions. We ended up with certain functional form of negative log likelihood. Questions on this? Food for thought. Think about some other distribution you may have started with instead of normal distribution. Laplace, student T. You could have used various other such distributions. That would give you something different. Right? And try and compute what you get as a negative log likelihood. It's a good candidate question for the upcoming quiz in the first week of September, the first 1/3 exam. We can go back to code. So I think that's the beauty of writing such, thinking of this in the probabilistic framework. Now, if you notice the code, I have a simple function, negative log likelihood of theta. Right? I compute the mu term, which is theta naught plus theta 1 into x. Right? I'm assuming sigma to be constant for now. I can create a distribution object, which is normal distribution with a certain mu and sigma. And I evaluate the log probability at my y's. Right? I was getting y's this way. My y's was fx plus noise. And I'm computing the negative log likelihood. Right? This expression is negative log likelihood. So I've again given you this on the platter when you have to solve the assignment, when you have to use gradient descent to optimize this. You already have the function. All you have to do is to write a gradient descent loop over this objective function. Right? And as we'd expect, so another thing which I always recommend doing is whenever you write such a function, do some sanity checks. Let's try some different values of theta. Let's assume that if I tried 0 and 0, right, that would be this line, right, a poor fit. Instead, if I tried out 1, 3, which is my ground truth parameters, right, I'd expect to receive, so I have much lower loss if I'd use the true parameters, 1, 3. Right? Are these the best parameters for this data set? How many think 1, 3 is the best set of parameters for this data set? Okay, how many think not? This is just linear regression, yes. Okay, how many think this is not the best set of parameters? Not? Why? Okay, if this data set is of size 100, if this data set were of size million, the true parameters would be pretty much reflected by the data sets from the sample, right? But because this is the smallest data set, so maybe the best set of parameters which describe this data set is very close to 1, 3, but not exactly 1, 3. Right? How do we see that? We create a contour plot, something like this. Right? Again, in the contour plot, I'm doing exactly what I did in the previous class, in the previous lecture. I repeatedly call this negative log likelihood function using different values of theta naught and theta 1. And I'm showing the very simplified version using 2 for loops. There are better ways to do this without using 2 for loops. But this is an easy way to understand for each different value of theta naught and theta 1 in this 2D grid, you're computing this negative log likelihood term, and then you're creating these contour plots. And it turns out that the optimal value of negative log likelihood is theta naught equal to 1.01 and theta 1 equal to 3.03. So not exactly 1 and 3, slightly different, and the best objective is also slightly different, not exactly what we'd get at 1, comma 3. Right? But if you notice, the good thing about this code is that I didn't have to specifically do mu equal to something. I specifically didn't have to do y minus y hat square like term, right? I only had to define the likelihood term. So going ahead, we'll be calling this as the likelihood term, which is normal, the likelihood distribution, which is normal distribution with certain parameters mu and sigma, and I can then get the loss for any given theta. So the mu is tied to theta. Therefore, if you build a computation graph and you do gradient descent, you would be able to optimize over the parameters theta automatically, right? Now, let's say that instead of using linear regression, I was using a neural network, right? Instead of linear regression, for the same data set, I was using a complicated MLP. What would change in this function? Anyone else? How would I need to change this function or the loss function if instead of linear regression, I were using a neural network? Someone else? Okay, Meet, what do you think? Cross. No, we're still doing regression. We're not doing classification. What would change? I think what may help you is that whenever you're trying to write such functions, it may additionally help to create a forward method. Forward method which works on x, comma theta, return x into theta 1 plus theta naught, mu equal to forward of x, comma theta. Fortunately, the code still works, right?
So the parameters will change. We have different parameters.
We only need to change the forward method. That is it. Instead of using x into theta naught, x into theta 1 plus theta naught, you need to do neural network dot forward of x. That is it. You need to do a forward pass of the neural network. You will get a mu from that, and that you need to put in this method. Nothing else changes. Right? So that's again the good part of writing code in this way. You are just describing the likelihood function. The forward method will give you the mu's, the most likely predictions, and you need to know some sigma and you'll be able to. And you can very easily see if we had an interactive plot like this. The true values were 1 and 3, right? And you'll see that as I increase theta naught, okay, this is run over the previous data sets. Let me run again. Right, so as I increase theta naught, you can see that the loss is decreasing in the contour plot as well as the fit is becoming better. And as I increase theta 1, I'm moving closer to the inner contours, and now my fit is better. Right, so that's exactly what we've been doing previously, but just that this is coming through the log likelihood, negative log likelihood term. Nothing new in that besides this. Okay, questions on this? So if you want to minimize negative log likelihood, you'll differentiate with respect to theta, you'll obtain theta hat equal to x transpose x inverse x transpose y. This is your theta MLE. Now we want to do the same thing, but for logistic regression. Right? So to understand logistic regression, I always want to go back to coin tosses because that helps us relate the Bernoulli distribution as well as the logistic regression function. So in coin toss, I've purposefully changed the variable of concern here. I'm looking at coin tosses. I'm given a data set of y1, yn, where each of yi is either 0 or 1. 1 indicating a head, 0 indicating a tail. What do we have correspondingly in logistic regression? What is the data set? D equal to what, what? It's tuples of x, y's, where x is a vector, y is again it's the 0 or 1. We're talking about binary logistic regression for now. So we'd be given the data set in this fashion, right? So I purposefully kept, as I'm mentioning, I've purposefully kept this variable also to be y, because in the coin tosses also we have y's which are either zeros or ones. In logistic regression also we have y's which are zeros and ones. In the coin toss, we said that the probability of getting a heads is denoted by, so heads is also class 1. It is denoted by this expression p of y equal to 1, which is given as theta. Right? We say that theta is indicating the probability of getting a heads, and then given a data set, we were trying to optimize, we were trying to figure out the MLE for theta. What do we have correspondingly in logistic regression? What line do you think we should write? You are given x's, right? So you'll have to somehow count for x's, and the model parameters of logistic regression are theta. You have to think of somehow tying theta, x's, and getting some y through that. Okay, Arjit, what do you think? What should be the corresponding line for logistic regression? We have to tie x's, yes. Yeah, we have a straight line, but what can I write correspondingly? So here it's a very succinct statement, p of y equal to 1 equal to theta. For logistic regression, my model parameters are still theta, and I have to account for input xi, which I didn't have to account here, and somehow I have to tie all of them up. So what can we write? Yes, for logistic regression, how will we do that? You're directly jumping. I want one step before that. What is the equivalent of this line? I think so. So again, I'm purposefully going slow so that each time you build up, you can see the correspondence between coin toss and logistic regression, because otherwise the jump seems a little high. Okay. Probability of y equal to 1 given an input x is the sigmoid of x transpose theta. Right? I think all of you knew this, but perhaps in this framework it was not very obvious to think. Right? Everyone clear on this? Probability of y equal to 1, predicting the class 1 given an input x is the sigmoid of x transpose theta. Why do we have the sigmoid function over here? Okay, Utkarsh. Okay. Right, you want p equal to y equal to, you're trying to compute p equal to y equal to 1 given x. X transpose theta is not going to be between 0 to 1, it can be anywhere. You want to squash that to something between 0 and 1, and therefore you apply the sigmoid activation. You could have used something else also, but sigmoid is one such activation which you can use. Right? So these two lines are fairly similar, but there is some different ways in which theta is occurring. In logistic regression, theta occurs firstly multiplied by x transpose. After that, you have to apply the non-linear activation to get something between 0 and 1. Whereas for coin tosses, you directly use theta. Okay. Next, based on the previous lines, right, we can say that for the coin toss, y is Bernoulli distributed with the probability of class 1 being theta. Right? This is what we had said. This is the Bernoulli distribution for coin toss. What can we similarly say for logistic regression? Harshit, what do you think? So let's go back to the previous slide. Probability of y equal to 1 equal to theta, right? One way to encode this is that y is Bernoulli distributed with probability of heads as theta, right? If you recall the Bernoulli distribution, it accepts as input the probability of class 1 or probability of success or probability of heads, right? And given a Bernoulli distribution, you'll get either zeros or ones, right? So probability of y equal to 1 equal to theta is the same as writing y is Bernoulli distributed with the probability of class 1 being theta. So the expression that you're seeing now is the same as this expression. There's just two ways of writing the same thing, right? What can we now write about logistic regression? Here probability of y equal to 1 given x was sigmoid of x transpose theta. So what can we write for logistic regression? Y is what? Ritik.
Probability of y equals 1 equals theta to the power y.
No. So I just want about the variable y. Similar to this expression, exactly similar to this. Bernoulli of sigmoid of theta, Bernoulli of sigmoid of x transpose theta, right? So here you think y is Bernoulli of something which is indicating probability of heads or probability of success or probability of class 1. Similarly, y for logistic regression is Bernoulli of the variable which is of a value which is indicating probability of success or probability of class 1, and that probability of class 1 is given as sigmoid of x transpose theta. Questions on this? You want me to repeat? Okay, I'll repeat. We go back. For coin tosses, we know that the data set is consisting of only y's, right? Each of the yi is either 0 or 1, which is indicating heads, which is indicating tails or heads. Logistic regression, we also have the input x. We're trying to learn the relationship between input x and the output y. That is important, but our y's are still either zeros or ones, class 0, class 1. So in that regards, coin tosses and logistic regression, both of them have the same y-like variables. They're both zeros or ones. For the coin toss, we know that the probability of getting a heads or class 1 is given by some theta. Right? We are defining this theta as the probability of class 1, y equal to class 1 being theta. Right? Similarly, for logistic regression, we want the probability of that a particular y observation would be class 1 given the input x. Now this is what we learned previously in the ML course. This is by definition from what we learned in the ML course. Probability of y equal to 1 given the input x is sigmoid of x transpose theta. Right? Sigmoid of x transpose theta think to be equivalent of this theta coming from the coin toss. Both of them you can just now substitute equivalently and you will have all the further answers. We can equivalently say that y is Bernoulli distributed with parameter theta for coin toss. For logistic regression, the equivalent thing is probability of y is Bernoulli distributed with the parameter sigmoid of x transpose theta. Right? Is the connection now slightly better? So don't feel shy and ask questions on this. This is the reason why I've tried to go slow. This is slightly tricky because we think it's easier to think in terms of the normal distribution, slightly trickier to think in terms of the Bernoulli distribution.
So why would we say that the probability of y given x is the Bernoulli distributed?
So we say the random variable y is distributed as per distribution. So that's the convention. Random variable is given as per distribution, and equivalently you can say this. So both of them are equivalent. P of y equal to 1, P of y equal to 1 equal to theta, and you're making certain assumptions here. that it's coming from the Bernoulli distribution. So this is perhaps the better way to always start with, right? But because we used to looking at P of y equal to 1 given x equal to sigmoid of x transpose theta, that's why I think this is easier to look. Right? So if you want, we can go back to the logistic regression slides and show that this is exactly what we'd seen. So there we started with this kind of an example. We have oranges versus tomatoes. We're trying to classify them. Our input is a single feature x. So I firstly change this plot to indicate y equal to 0 and y equal to 1. My oranges are y equal to 1. Right? Now we said that we could have learned probability of y equal to 1 given input x as some theta naught plus theta 1 x, which would have been a line. Right? But the central thing which we were trying to model here is probability of y equal to 1 given my input x. Right? We said that that could have been theta naught plus theta 1 into x, but that's having problems because one, it is not bounded. Secondly, any outlier would just make this line go crazy. Like an outlier like this would change the decision boundary very significantly. Whereas an ideal boundary might have been something like what we're seeing currently. So this is a step function which is not continuous. In order to get something continuous, we could have used the sigmoid over x transpose theta, which we get from linear regression, but we squash it to something between 0 and 1. So therefore, we ended up writing probability of y equal to 1 given x to be sigmoid of x transpose theta. Right? And in this case, I've written for the entire vector, therefore it's capital X theta. But this is the same expression which we have now written. Probability of y equal to 1 given x is sigmoid of x transpose theta. So the Bernoulli distribution accepts as argument the probability of success. Right? In coin toss, the probability of success is theta. We've just defined it. For logistic regression, we say that the probability of success or heads of class 1 is sigmoid of x transpose theta. Right? Now is everyone clear? Okay. So the Bernoulli likelihood for the coin toss is given as likelihood of theta, which is product of I equal to 1 to n of theta to the power yi into 1 minus theta to the power 1 minus yi. Right? Again, substitute, consider a single example if this causes confusion. Single example, let's say yi, only y1. If y1 is 1, right, then what is the likelihood of theta? Only theta, right? Instead, if yi is 0, which means it's a tails, the probability of obtaining a single tails is 1 minus theta. The probability of obtaining a single heads is theta. If y1 is heads and y2 is tails, the probability of obtaining 1 heads and 1 tails is theta into 1 minus theta, which you are able to get. Right? So this is a likelihood for the coin toss, theta to the power yi into 1 minus theta to the power 1 minus yi. Yi is your observation, which is either zeros or ones. Theta is your probability of heads. Right? What is the equivalent in logistic regression? Sigmoid of xi transpose theta to the power yi into 1 minus sigmoid of xi transpose theta into 1 raised to power 1 minus yi. Right? The easiest way to remember this is through this slide, that theta is corresponding, theta in coin toss corresponds to sigmoid of x transpose theta in logistic regression. Everything else will just follow. So likelihood now becomes theta to the power yi into 1 minus theta to the power 1 minus yi. Similarly, for logistic regression, it becomes sigmoid of xi transpose theta to the power yi minus into 1 minus sigmoid of xi transpose theta into power 1 minus yi. We can compute so we can now, instead of always writing that big expression in terms of sigmoid of something something, let's try and write something simpler. Let's write yi hat equal to sigmoid of xi transpose theta. Right? What is the value that yi hat can take? Between 0 and 1. It is trying to encode the probability of obtaining class 1, right, given the input x. So if we just put yi hat to simplify our life, we can then write the likelihood as likelihood of theta for the logistic regression problem as yi hat to the power yi into 1 minus yi hat to the power 1 minus yi, and the product over that from I equal to 1 through n, right? So we've just done the substitution, nothing beyond that. Log likelihood for coin toss is you convert the products to summations, and then you can write it as I equal to 1 to n yi log theta plus 1 minus yi log of 1 minus theta. So we saw this in the previous lecture when we were trying to find out the theta MLE for coin toss, right? Correspondingly, what is the log likelihood for, can you correspondingly in your notebooks, I think if you do that, that will be giving more confidence. Can you write down the log likelihood for logistic regression just as following of this, but instead of using terms containing theta, just use terms containing yi hat. Let me go back to the previous slide. So first just note down this function L of theta for logistic regression, and then just take the log of this. Okay, can we write it something like this? Log of L of theta for logistic regression to be a summation of I equal to 1 through n for the n samples, yi log yi hat plus 1 minus yi log of 1 minus yi hat. Right? And now we compute the negative log likelihood, which is just multiplying by minus. Now does this term look like something you've seen earlier? Cross entropy loss, right? So we've gone from a very simple assumption of Bernoulli likelihood, and we've been able to obtain the binary cross entropy loss. Right? You didn't have to come up with justifications for why this looks like a good cost function, that if yi is high and yi hat is low, then this is giving you a very high cost. We started with the very fundamental assumption that the distribution is Bernoulli distributed, right? Like we did for coin toss. Okay, question in this? I think this still remains slightly complicated to understand unless we write a bit of code which shows the generative process. I think after that only things start becoming slightly easier. So let's show you some code. For logistic regression, I first create some x, which is uniform between -5 to 5. I create a true theta, which is -10, 4. I create a p, which is sigmoid of x transpose theta, right? What values does p take? Zeros to ones, right? And then I plot x to p of x, right? This is indicating the probability of a sample being class 1, right? This is just indicating the probability of sample being 1. At this point, the probability of sample being 1 is very high. At this point, the probability of sample being 1 is very low. Is the probability of sample being 1 here 1? No? Why not? Almost 1? But almost 1 is almost 1 equal to 1? So if we were to use, let's say if I were to pick up some point around here, right, and draw samples from it, am I guaranteed to get ones? No, because it's not exactly 1, right? So this may be probability of getting a 1 could be 0.95, but that is not 1.0. So there is still 0.05 proportion of chances where you will be able to get a tails. Another interesting way to look at this problem could be to look at different parameter spaces. So in this case, I have -10 to 4, and if you can notice, the sigmoid is slightly shifted towards the right. If instead I had -1, 4, it seems to be now much closer to 0, like this change occurs to be much closer to 0. And instead this was minus, so previously I had minus 10 comma 4, but instead if we had minus 10 comma 0.1, what change happens? The slope, the change from the 0 to 1 is now very slow, whereas previously the change from 0 to 1 was very sharp. Right? What are the true parameters we are using? 4. Right? So the change is very sharp. If you want to go further, it is now becoming as very similar to the step function. Make it want to go slightly higher, you can see even more. Right? So if you can see how the probability, this is importantly only telling you the probabilities of class 1. This is not the classification boundary. Right? The classification boundary you can draw by thresholding this as at 0.5. Right? That's the process which we followed in the previous semester's course. Now, given certain x values, given certain true theta values, once you put this function x transpose theta and a sigmoid over that, you will get the probability of it being class 1. For a corresponding x value, you get how likely is it to belong to class 1. You can very clearly see that for x's which are close to 4, they are much more likely to be class 1, and for x's which are, let's say, close to minus 4, minus 3, minus 2, they are much more likely to give you the class 0. Right? Just based on this. But much more likely does not mean always. So therefore we use y. Our y is Bernoulli distributed. So this is now exactly coming back to the slides. So slides said that y is Bernoulli distributed with sigmoid of x transpose theta. That's the generative process. Go back to the code. Y is Bernoulli distributed with the probabilities of p, where p is sigmoid of x transpose theta. Right? And interestingly, if you'll see y, even for certain high values of x, there are certain y's which are 0. Right? Even though the probability of getting a class 1 was very high, you could still get a 0 from it. Right? Because it's not exactly 1. A coin which has a probability of heads to be 0.95 can give you a tails. Similarly, you are obtaining here. And if you were to then obtain some data set from this, you observe that there are certain points. There is this particular point which is predicted to be class 0, even though the probability of heads was of class 1 was very high. So this is the underlying data set that we have. Now, again, as I was mentioning before, the good part of writing such code from the probabilistic perspective is that does this function look very similar to previous function which we had? We define certain value p equal to torch.sigmoid of theta 0 plus theta 1x. We could have perhaps just put this in a forward function. A forward function would have done x transpose theta and taken an activation over that. Right? And then I just pass whatever parameters I'm getting through that to a Bernoulli object, Bernoulli distribution, and then find out the negative log likelihood for the data. Right? The expression is, the last line is always the same. This minus this dot log prob of the y dot sum, irrespective of what we had written. So nowhere I had to write the sophisticated cross entropy loss over here, but it will naturally come as a consequence of trying to minimize the negative log likelihood. Right? So if I again do some sanity checks over this, okay, I need to run the code again. So this time I got samples which were, none of them were on the other side. But maybe if I do this again, this time I get some samples which are slightly noisy. I run the negative log likelihood function for some theta. For the true theta, again, my loss, my objective is much lower than if I pick up any random theta, which is something you should always do as a sanity check. And then we can correspondingly also create the contour plot. Right? So this is the contour plot. This is a convex function. This is a convex objective. So you'll have a single minima around this. And this is the minima that I've obtained from this grid search like perspective. If you notice this, this is theta naught equal to close to minus 10 and theta 1 close to 4. So we've been able to recover something very close to the true parameters through this minimization problem. Of course, I've not done the minimization, but I've just done grid search over this. Now, another interesting thing which many libraries allow is, let's create another version of this function. Let's call this using logits. I'll not have the sigmoid. I'll call this logits equal to this. This is the difference between the two functions, right? So I'm calling something known as logits to be x transpose theta. What is my range of logits? Minus infinity to infinity, right? And I can directly pass it to the Bernoulli distribution objects, that logits equal to logits. Previously, if you wanted to be more precise, we should always write probs equal to p. You could either pass the probabilities, which are numerically poor conditioned, because you have to run a sigmoid over that. Right? But why do that when you can directly just pass in the logits function? So whenever we write such functions, we should always do a sanity check. So we should always, let's say, copy this and check whether the numbers that we are getting are same or not. Fortunately, the numbers that we're getting are the same, right? But wherever possible, we should use the latter. Right? Directly in terms of computing logits instead of computing probabilities. It's numerically better conditioned. You have lesser steps in the computational graph. Right? So you get various advantages. Okay, so that's all I had for today's lecture. Any questions? If not, we can quickly summarize. Any questions? So for today's lecture, what we discussed was two problems. We discussed MLE for linear and logistic regression. The important thing here is to understand the generative process, which is if we just understand this graphical model, we'll be able to understand MLE fairly well for such distribution, for such problems. For linear regression, we said that we assume that yi is normally distributed with the mean of xi transpose theta and a certain sigma which is independent of the data as well as constant across all the data terms. And through this, we are able to model yi to be normally distributed with xi transpose theta with variance sigma square. And if we maximize the log minimize the negative log likelihood, we'd be able to obtain the parameters as the loss function to be the equivalent to sum of square or mean squared error. For logistic regression, we took the example with the similarity. We wanted to look at the similarity between coin toss and logistic. Both of them we used the output variable y, which could be zeros or ones. For coin toss, we said that the probability of y equal to 1 is given as theta. For logistic regression, probability of y equal to 1 is sigmoid of x transpose theta. After that, we can just write y is Bernoulli theta for coin toss, and we can write y is Bernoulli of sigmoid of x transpose theta, or y is Bernoulli of logits equal to x transpose theta, which is a better or easier way to represent. And beyond that, we can compute the log likelihood. It comes out to be, the negative log likelihood comes out to be equivalent to the cross entropy loss function. Good. So in the next class, we'll discuss about when we have certain priors available and how does that relate to regularization in machine learning. The assignment is due tomorrow, I believe, and we'll set up the assignment vivas also. Okay, thank you.